Hi, my name is Chenfenfu Jiang. Together with Professor Norman Badler and Stephen Lang, we represent the computer graphics group at the Sixth Center for Computer Graphics. So in addition to PhD research, our center also directs undergraduate and graduate programming graphics. We mostly focus on physics-based animation, which uses applied math and computational physics, solves partial differential equations for simulating physical effects in animations or visual effects like hair, clothing, water, smoke, fire, snow, sand, muscle flesh, and so on. Our technique has been used in Hollywood products like snow in Frozen, water in Moana, and other different physical effects in various animations. And more recently, we have been working on things like generating effects for fracturing food materials, and also extreme deformation of elastic objects, or predicting avalanches, simulating fluid dynamics, and also complex fluids like foam and creams, or thermal effects with phase change and solid fluid coupling. So to celebrate Halloween, we simulate smashing pumpkins, and for fun, we simulate breaking watermelon. These are for graphics applications. But for science, our simulations have also been verified against real-world data and can actually predict avalanches in geophysics with simulations matching the real experiments, thus having impact in computational science in large. And when we simulate the effect of temperature, we can melt things from solid to liquid. So this also relates to 3D printing and computational manufacturing, where we can use computational models to predict how things are manufactured in a laser-induced printer. More technically, we are focusing on the following aspects of simulations. The first is adaptivity. For example, this is an hourglass simulation. Since we're only seeing the surface of this sand flow, we can adaptively refine the particles near the surface and coarsen the regions inside. And we can also explore temporal adaptivity by choosing different time steps at different regions of a simulation of certain materials. This way, you're really concentrating the computational resource at certain regions. We also look at time stepping, for example, letting the fluid dynamics to preserve energy better, so you get more turbulent and accurate computational fluid dynamics effects. And we also want to capture more intricate shapes, for example, such as this fiber direction response of inorganic materials like this orange. In addition to the numerics, we always look into simulating more versatile phenomena. So here's a result of a sediment transport experiment with very turbulent water, and the water interacts with little dirt or sand soil particles. High-performance computing is also a major focus. We run our simulations from the consumer-level workstations or desktop PCs to multi-GPU supercomputers and clusters, collaborating with HPC centers and national labs. And finally, we also collaborate with the GRASP lab closely with the vision and robotics faculty by combining differentiable physics-based simulations with machine learning and robotics for designing better and smarter robots like this soft robotic hybrid aerial vehicle.